Thank you, Chris, and thank you all of you for coming. And I'm Shankar Nair from Tang & Associates, and this is the 2007 T.R. Higgins Award Lecture. The subject is a new approach to design for stability, and specifically as reflected in the stability and analysis provisions of the 2005 AISC specification. I'm going to take this opportunity, though, to do more than just introduce the new specification. I'm going to try to demystify the whole process of design for stability. Too often, or for too long now, I believe structural engineers have been designing for stability more or less by rote. I mean, it's a black box. You follow the equations and you get your answers. And that's not the way we should be doing it. I'm going to try to show you just why we do what we do in structural engineering, in stability. So to do this, I'm going to be going through several steps. I'll talk briefly about what is stability, how have we been designing for it, and why do we need to change? What's wrong with the way we've been doing it all these years? And then with that, I will lead into the new approach. Let's begin at the beginning. What is stability? Well, stability is buckling, or rather the prevention of buckling. That's the most obvious definition, I think, that most people would come up with. But now, what do I mean by buckling? What you see in this picture, on the left you see that is a structure, a very basic structure, subject to a compressive load that causes no lateral displacement. And then down at the bottom here, we see a single member, again subject to a compressive load, P, that causes no lateral displacement. And then that little graph on the right shows the displacement of applied load, compressive load P, to lateral displacement. And you can see that there is no lateral displacement. And as we increase P, there is still no lateral displacement until we get to some magic number called the critical load, P sub CR, at which time we get so-called bifurcation. We get sudden, uncontrolled lateral displacement. And this is the concept of buckling. Well, buckling of this type is a theoretical abstraction. It is not real. It does not happen in real structures. In the real world, there is no such thing as buckling. Now, that may come as a surprise to you, but I'll show you in a minute why I say that. Now let's talk about another concept. This is the concept of amplification. Again, this is the same structure we saw before with a compressive load on it. And you can see that that force P, the compressive force, causes no lateral displacement. But now, instead of compressive force, let's put a lateral load on it, F. And for both the structure and the individual member, you can see how you do get lateral displacement roughly proportional to the load. Now let's combine this lateral displacement, which does cause a lateral displacement, the lateral force, which does cause lateral displacement, and that compressive force. We see that when we combine the two, even though P by itself does not have any effect, when we add P and F, we get a different response than with F alone. You can see on the picture on the right that the response is different with and without P, even though P by itself causes no lateral response. Or looking at the two pictures together here, the upper pictures on the left are lateral load alone, the lower pictures are lateral load plus the compressive force. And you can see in the graph on the right how with P, applying the compressive force increases the lateral displacement caused by F from Y0 to Y. Now, or another way to show that is in a curve like this. This is for a constant F. For any given value of F, this is the relationship between the compressive force P and the lateral displacement. We have this beginning lateral displacement of Y0. That's what you would have with no compressive force. Then as you add compressive force, the displacement increases. And while buckling is a theoretical abstraction that does not happen in real structures, amplification is real. Amplification is this fact that Y, which is the displacement when you combine the compressive and lateral load, is greater than Y0, which is what you have when you have lateral load alone without the compressive force. And this amplification is a real phenomenon. Now, Y0 may be the result of a lateral load, as you see here, or an initial imperfection. You could have a structure with an initial outer plumbness or outer straightness of Y0. Now, when you put a vertical load on this or a compressive load on this, you can see that that Y0 will increase to Y. And that, again, is amplification. So, in this picture, you see how the theoretical buckling phenomenon is represented by that line on the right, where you get no lateral displacement up to some magic value of P, and then you get sudden bifurcation, sudden uncontrolled displacement. Amplification, though, you start with a Y0, which could be a displacement either caused by initial imperfection or a lateral load, and then as you add the compressive force, that displacement increases. Now, buckling is not a real phenomenon because in the real world, there is always a Y0. Every real member or structure has some initial imperfection, even if it's very small, or it has an initial lateral load, or both. But there is always at least an initial imperfection. So the actual response curve of any member will never look like that one on the left, but it will look like the curve on the right. You always start with some initial imperfection, and then you increase from there. And what that means, though, is that failure of a frame or a member loaded in compression always involves lateral displacement and flexure, because anytime you have lateral displacement, you always have flexure. So there's no such thing as a pure compression failure. Even if the load you apply is pure compression, the actual failure is going to involve a lot of flexure. And let's see how that works. Consider, this is now a theoretically perfect column, plumb and straight. And let's apply a vertical load on it. Axial, vertical. You get pure compression, no flexure, and you see what the relationship looks like in that graph on the right. And that you can keep increasing P until you get failure by yield, which would occur at area times yield stress, or you could get failure by buckling, which happens at pi squared EI over 4L squared. That's a very familiar equation. So this is how a theoretically perfect column would work when you put a vertical load on it. Pure compression, no flexure until failure by yield or buckling. Of course, this is not what really happens, because in a real column, you always have some initial out of plumbness. And for the moment, let's forget about out of straightness and just look at out of plumbness. Let's give it initial out of plumbness y sub 0, which is, you see it also in this picture on the right. That's y sub 0. That's where we are starting, and that's y sub 0. That's the imperfection. Now, when you put load on it, you can see that that load is going to cause compression and flexure. And as you increase the load, the flexure gets more. And generally, the flexure will increase more rapidly than the compression, and that keeps going like that until the strength limit. And this maximum load that this column, maximum vertical or compressive load that this column can sustain is that P sub n. That's the point where this curve starts dropping off. What is important to note, though, is that even though this was a nominally vertical column under vertical load, at the point of maximum load, there is a tremendous amount of flexure in this. In fact, depending on the L over R and so on, you may have more flexure, more flexural stress than compressive stress at this point of maximum load. So the point is, failure of a real member loaded in supposedly pure compression is not by crushing in compression at area times yield stress, not by buckling at pi squared EI over KL squared, but by compression and flexure. And it will always be a phenomenon like this, where you always have flexure at the point of failure, or at the point of maximum vertical load or compressive load. And I was showing a cantilever column because it's a convenient type of structure to deal with, but the same thing works for a frame. The frame always has some initial imperfection, so when you put a nominally compressive load on it, you get lateral displacement, and at the point of maximum load, failure, when P sub n reaches its limit state, its limit, you are going to have a large amount of flexure in those columns. Or look at an individual member. The initial condition in that member is always, as you see on the left, there is always some initial imperfection of y sub 0, and as you load it, that will increase, and you keep getting flexure, and at the point of maximum load, limiting load, which is the point of failure, it is going to be largely a flexural failure as well as a compression failure. So, the point is, failure of a frame or member loaded in compression always involves flexure, even though it's nominally a compression member loaded in compression. And the response will look, not the idealized response, but the actual response. That's how the structure will actually respond. But to capture that actual response requires a second order analysis. For instance, if you look at this frame we looked at before, where the lateral load causes a displacement y sub 0, but then when you add the compressive force, it goes up to y, a linear analysis will not capture that behavior. In fact, the linear analysis will show what you see in this picture on the right. It will show, regardless of what the compressive force is, it will show the displacement is just y sub 0. That's what it will show. The second order analysis, though, will capture the actual behavior. That's how it behaves. As you increase p, the displacement increases. And of course, if instead of the initial lateral load you had an initial imperfection of y sub 0, then again, and suppose you did model that initial imperfection in your analysis, the linear analysis still won't give you the correct answer. It'll give you what you see in that picture, the broken line, while of course the second order analysis will give you the correct answer, but only if you included that, that y sub 0 in your analysis. You have to model it in the analysis. So, and of course, if you had no lateral load and you did not, and you neglected the initial imperfection, you did not include it in the analysis, then it doesn't matter what type of analysis you do. You're going to get that straight line response. You're not going to pick up any lateral displacement. So, these are the various responses we have seen in those last few slides. Now, the second order analysis gives the correct response, but clearly, correct prediction of response also requires the correct y sub 0, including the initial imperfection. If you neglect the initial imperfection, you're just going to get this straight up and down line, which is not the correct response. You need to model y sub 0 correctly in your analysis. So, for correct prediction of response, you need a second order analysis, and you need the correct y sub 0, including imperfections. Now, just to take a little detour here, what do I mean by second order analysis? Now, a second order analysis can be either a direct second order analysis or so-called amplified first order analysis. Now, what does that mean? Well, you remember this concept of a critical load, and I said it wasn't real, but it is useful, as we'll see in a moment. This shows the first order for a given combination of lateral and vertical load. You can see the first order response is y sub 0. The correct second order response is y. Well, the two are related to each other very closely by this equation, which is certainly an equation everyone in this room has seen. That amplifying factor 1 divided by 1 minus p over p critical. So what this tells us is that if you know the first order response and you know the critical load, even though that critical load is a theoretical quantity, it's not real, you can apply this equation to come up with a very good estimate of second order response. And this, of course, is called amplified first order analysis. This is the familiar B1, B2 method of second order analysis that we're all familiar with from I think at least the last 2 cycles of specification in AISC. And in this, B1 gives you the amplifier for the member and B2 for the story of a structure. Of course, second order analysis, direct or indirect, is not enough. You must emphasize that. To get the correct response, you must also have the correct y sub 0, whether it is due to lateral load or an initial imperfection. You must model the y sub 0 or you are not going to pick up your correct response. And a new concept now. To get the correct response, you must also adjust for stiffness reductions due to inelasticity. What does that mean? Well, in a typical road member, any kind of road member, you're going to have a residual stress within that member due to the manufacturing process of the order of 3/10 of yield. When there's no external load in the member, you have tension and compression, all of it balancing out within the section, of a magnitude of about 3/10 of yield. What that means is that part of the section will start yielding when the stress due to applied force and moment reaches 7/10 of yield. So when P over A plus MC over I approaches 7/10 of yield, some part of that cross section is going to yield. And when that happens, the overall stiffness decreases. And of course, when stiffness decreases, you get more second order effects and so on. And you've got to somehow account for that in your analysis if you want to be accurate. You can't assume that the member remains perfectly elastic all the way to until P over A plus MC over I gets to be yield stress. No. When it gets to be even 7/10 of yield, you're starting a stiffness reduction. Okay, now let's change gears for a moment, go into something else, or as Monty Python used to say, now for something completely different. Well, let's look at the compression strength of a single member. And again, let's first look at a perfect member with a load P on it, a compressive load. Again, for this perfect member, the strength of the member would be the lesser of pi squared EI over L squared, or area times yield. And graphically, that would look like this. That upper line is the yield-controlled strength, and then that parabolic curve is the buckling controlled strength. This is what it would look like for a perfect member, with no imperfections, no residual stresses. For a real member, with a normal amount of imperfection and residual stress, it looks like this. When you adjust the curve for imperfections and residual stress and inelasticity caused by residual stresses, this is how your response looks. And this adjusted curve, this is the familiar column strength equation. This is the so-called compressive strength for flexural buckling in the specification in Chapter E. So those familiar column strength equations that we've seen for generations, as first it was, I think, first developed, some more than 50 years ago, and the current form of it is in the current Chapter E, that represents this kind of behavior. It represents the strength of a column with imperfections and a normal level of residual stresses. And that curve, it's important to note, represents failure not by pure compression, but by compression and flexion. Even though the applied load is compressive, the failure is not by yield, not by buckling, or I should say not by pure compression and not by buckling, but by a combination of compression and flexure. In other words, this is the kind of failure that is represented by each point on that strength curve. You're starting with a member that is slightly imperfect, with that imperfection y sub 0. You're applying more and more load on it, and your limit is how much of load P can that sustain before it fails, and it fails in a combination of compression and flexure. So this curve again represents failure by compression and flexure, not by bifurcation, buckling, and not by yield, except when L over R is 0. Then you do get yield over the whole section. That's the only time you get it. Okay, with that bit of background, let's talk about how have we been designing for stability. What is the traditional method? And by traditional method, I mean before the latest specification, before 2005. Well, the first step is we find forces and moments in all members from a second-order analysis, neglecting imperfections and inelasticity. Traditionally, we have not considered imperfections and inelasticity in the analysis. And the second-order, you were always required to do a second-order analysis. Not everyone realizes that. But that second-order analysis could be either a direct, rigorous second-order analysis or the old B1, B2 method. That is second-order analysis. So, but one way or another, you've got to do a second-order analysis, either direct or by amplifying a first-order analysis by B1, B2. Then, once you've got your forces and moments, you check the member capacity using the column curve or the strength equation that includes the effects of inelasticity and imperfections, which is the usual column curve. In other words, this one. Now, how does this look when you, let me try to show it graphically or diagrammatically. So we start with the applied loads, do a second order analysis to get the member forces and moments, and in that analysis we neglect imperfections and inelasticity. Then we compare this member demand, the P and M, with member capacity. And of course, for member capacity we use the usual column strength equation, which includes imperfections and inelasticity. The big question is, do these compensate? We're neglecting imperfections and inelasticity in the analysis, and we're including it in the member capacity, as we should. Well, they clearly do not compensate, because by neglecting imperfections and inelasticity in the analysis, we are understating member demand. When we I think you can see that quite clearly, that if you neglect imperfections, you're going to get forces and moments, or at least moments that are less than what they should be. While this including imperfections in the member capacity gives you the correct member capacity. So you're comparing an understated demand with the correct capacity. So there's clearly something wrong here. It doesn't work. Well, fortunately, this error caused by understatement of member demand is important only in structures subject to side sway. And let me show you why. This shows, just a idealized structure that is not subject to side sway. You can see it's braced against side sway. You can see that the fact that you have this initial imperfection y0 will not greatly affect the forces and moments within the frame, because the effect of that imperfection is just carried into the bracing. But suppose it was unbraced, not braced against side sway. Now you can see that because of that y0, I think you can just see it intuitively, how that y0 will affect the forces and moments in that frame, obviously. So this error that we have traditionally been making of neglecting imperfections and inelasticity in the analysis, that understates member demand in structures subject to side sway. So what do you do about that? Well, we compensate for that by using k greater than 1 on the capacity side of the equation. Now, many people who've been using this approach for several code cycles or specification cycles, they've assumed or they've believed that the reason you use k greater than 1 in your member capacity check is to account for second order effects. It is not true. No, you're required to do a second order analysis anyway. The reason you are using k greater than 1 on the capacity side has nothing to do with second order effects. It is to compensate for the fact that you have neglected imperfections and inelasticity in the analysis. That's why you use k greater than 1 on the capacity side of the equation in the traditional pre-2005 spec. Let's see how that works. I know this sounds very counterintuitive, and I think even after this example it'll still seem counterintuitive, but that's the way it has been done. Consider a cantilever column with a vertical load on it. And now let's apply the conventional pre-2005 analysis design approach to this. Step 1, do a second order analysis, neglecting imperfections and inelasticity. So when you do a second order analysis of this vertical column under the load P, what is the result? You find an axial force of P in the column and 0 moment, because you're neglecting imperfections as you always did, as you did traditionally. So any kind of analysis, first order or second order, will give you a base moment of 0. So you have no moment, axial force. Now design this member for force P and 0 moment using the column strength equation, the usual column strength equation, but do it with a k of 2. That is what you were required to do traditionally. And of course this is the equation you're using. You're using this curve adjusted for imperfections and inelasticity. Now this curve does not represent a straight member. Remember, this traditional column curve represents the strength of a member that is slightly out of straight, like that, by y0. So in effect, when you design this straight member, you are actually not designing a straight member, you're designing this one. And this is really the same as the actual cantilever with some outer plumbness and initial curvature. So by the back, sort of in a very roundabout way, you have in effect analyzed and designed your actual structure, which is outer plumb, even though you didn't explicitly consider it. And even the numbers work out, because the amount of out of straightness implicit in the strength curve, in the column strength equations, is about the length over 1,000. And here the length is 2L, where L is the height of the cantilever, so 2L over 1,000. And the amount of out of plumbness that you would normally want to consider in a column is the code of standard practice requires that the tolerance be, or that the maximum out of plumbness be less than L over 500. So that is what you would normally consider as the limit on out of plumbness, and those are the same. So everything works. It's very roundabout, and it may seem counterintuitive, but the system works. This process of neglecting imperfections and inelasticity in the analysis, but then compensating by using k greater than 1 on the design side, it seems to work, but there are problems. The first obvious problem is that this process tells you that your base moment is 0. Using the conventional pre-2005 specification, you could analyze a vertical column with just a vertical load on it, and the analysis will always tell you your base moment is 0. But you know in reality it isn't, because actually you do have some initial out of straightness, and you know the failure is going to be mostly a flexural failure with a tremendous amount of moment at the base. Unless your L over R is 0, unless the zero height column, you're going to have flexure. But this process doesn't give you, but the traditional process didn't tell you what that moment was. So the conventional design process does not include the correct moment at the base in this case, or looking at it in general. This process, we neglect imperfections, that understates the moment, so we compensate in the column design by using k greater than 1. That will give you the correct column size, but it does not give you the correct moments. And if you do not have correct moments, you're going to end up with under-designed beams and connections. So this conventional design method for stability indicates incorrect design moments, and it's generally an unconservative error too. Another problem with the conventional design approach is that it requires calculation of k. Question is how? I think most of us are familiar with the Sidesway uninhibited alignment chart for column effective length, and people, I think, you have been using this for a generation to calculate k in your structure, in the columns in your structure. Well, the commentary to the AISC specification lists 9 conditions for the applicability of this chart. And number 8 of the 9 says the assumption that this chart is based on is that all columns buckle simultaneously. What does that mean? Well, it means that the ratio of the column force P to pi squared EI over KL squared must be the same for all the columns in the story. Is this true? Is this ever true? Well, it can be true. For instance, if you have a frame like this where the applied load is roughly proportional to the stiffness and also this, the restraint conditions at both ends of every column are the same, okay, maybe you could use the alignment chart. But as soon as you have columns with different support conditions, different restraint conditions, now this is no good for the alignment chart. Or if you have columns with no load on them, again, this is no good because those columns are not going to buckle like the others. So they're not all going to buckle simultaneously. Or this is a plan view now. This is no good for the alignment chart because you have those leaning columns in the middle that don't buckle like the others. Or even without that, you have these frames in 2 directions depending on which way you're looking at the buckling. They will not all buckle simultaneously. And for something like this, just forget about it, where you have, for an unsymmetrical structure. Now, people in earthquake territory say, oh, we'd never have a structure like this. But in low seismic zones, it's quite common to have structures that look like this, where you put in bracing where you can, and then you make up the overall stability with moment frames in other areas. And there's no logical way you can apply the alignment chart to get K for a situation like this. So the point is, few real-world buildings meet the conditions for applicability of the alignment chart. I have to pretty much put an X through it. So I asked, how do we calculate K? Well, how indeed? I really don't know how to do it. I don't know if anyone calculates K correctly for a 3-dimensional real structure. So we've seen 2 problems with the conventional approach. Another problem is that, as I said, we are doing a second-order analysis, and then for an unrelated reason, we're also using K greater than 1. And this combination, even though there is logic behind it, it can sometimes lead to an overly conservative result. So these are 3 very basic problems with the conventional stability design approach that we've been using for many years, through at least a couple of code cycles. And all of these are caused by this process of neglecting imperfections and inelasticity and then compensating for it by using K greater than 1. Well, suppose we included imperfections and inelasticity in the analysis. Then all these problems go away, the need to use K greater than 1 goes away, and all of these problems go away. And this method, where we include imperfections and inelasticity in the analysis, is the new direct analysis method in the new specification. And this is how we do it. This direct analysis method. You do a second-order analysis and include imperfections and inelasticity in that analysis. And once you do that, you can use K equals 1 in the member capacity check. And of course, where it says include imperfections and inelasticity in the member capacity calculation, that might sound complicated, but no. All that means is use the usual column strength equation. That's all. And you're covered. This is the direct analysis method, and that's the basis of the new specification. Okay, with that background, let's go specifically into the new stability and analysis provisions of the new 2005 AISC specification. Chapter B of the specification has requirements, the general design requirements. And it doesn't tell you much about analysis. All it says is the design of members and connections shall be consistent with the intended behavior and the assumptions made in the structural analysis. Now, in some material, for instance in concrete, ACI goes into a great deal of detail about how to analyze your frame. They say things like use center-to-center distances of members, but then back off your moment to the face of the column and things like that. Now, AISC has decided not to do that, and I think that's a wise decision. Leave that to the engineer. Leave it to the engineer's judgment as to how he does his analysis, but just make sure the analysis and design are consistent with each other. That is the basic approach in AISC. And that works, except when you get to stability analysis and design. Analysis and design are so closely intertwined that you really can't separate them. Given that AISC is giving you design rules, it also has to give you the analysis rules that go with that. So let's go through what AISC tells you about stability analysis and design. And basically what it says is the specification in Chapter C specifies that the design of the structure for stability must consider various effects. And those effects are flexural, shear, and axial deformations of all members, all component and connection deformations that contribute to lateral displacement. No surprise there. It just says you've got to analyze your structure accurately. You have to consider P capital delta effects, which is the effect of load acting through the displaced location of nodes in the structure. P small delta effects, which are the effects of load acting on the deformed shape of members. Geometric imperfections, both member shape imperfections, which is out of straightness, and also node position imperfections, which is out of plumbness. And stiffness reductions due to residual stresses. And once you've considered all of those effects, then the member can be designed using the provisions of the provisions for individual members from the various individual member chapters of the specification. And the specification now tells you explicitly that any method of analysis and design that considers all of these effects is permissible. So you can invent your own method as long as it considers all of these things in some rational, logical way. And then, these first two are general analysis requirements. AISC doesn't really tell you how to do it. Any engineer, I suppose, is expected to find his way through that. But then, for those who don't want to invent their own method of accounting for all these things, AISC does provide you with 3 specific prescriptive methods of accounting for these 4 effects: P deltas, geometric imperfections, and residual stresses. And of course, the most powerful and most general of those methods is the direct analysis method, which is in an appendix as it happens. It's not in the main body, but the main body refers to it as the default method, the method that's applicable in all cases. And this is applicable to all structures. It does not distinguish between brace frames, moment frames, shear wall systems, combinations. It makes no difference. It's just a general method of analysis and design for all structures, the direct analysis method. And let's see how it accounts for these different effects that you were required to account for in your analysis and design. For the P delta effect, you're supposed to use a second order elastic analysis that considers both P cap delta and P little delta. And for that, you can use a general frame analysis method that considers second order effects, or you can use amplified first order analysis. The old B1 and B2 method is still perfectly acceptable as a method of second order analysis. The thing you must always remember when looking at the specification is that first order analysis amplified by B1 and B2 is second order analysis. So anytime you're told to do a second order analysis, you can do a first order analysis and then amplify it by B1 and B2. That gives you a second order analysis. Okay. One exception is that P small delta can be neglected when the member axial forces are below a specified level. So that's how you take care of P delta effects. Now, with geometric imperfections, this is something we had never considered in the past. For geometric imperfections, you apply a so-called notional load. And let me tell you what the notional load means. Where the vertical load applied to the story of a structure is y sub I, a notional load is a lateral load applied at that story as a fraction of that vertical load. And the fraction you are asked to apply is 0.002, which is 1/500th of the vertical load as a horizontal load. Now this 0.002 y sub I notional load is equivalent to an initial out of plumbness of 1 in 500. And I think intuitively you can see how the two are equivalent. In its effect on the moments and shears within the frame, you can see that putting that horizontal load of n sub I of 1/500th of the vertical load has the same effect as actually tipping your structure over by 1 in 500. I won't go through the math, but I'm sure you can see how that works and you can work it out for yourself. And then the specification also tells you that you can use a lower factor than 0.002 if you can justify that by saying that the actual anticipated out of plumbness is less in your structure than 1 in 500. I don't recommend that actually, because 1 in 500 is not a very large out of plumbness. It's only about 1/4 inch and 12 feet. But if you have reason to know that your structure is going to be more plumb than that, you can use a different number there. Okay, now logically, these notional loads should be additive to other lateral loads in all cases. After all, it's always there. Whether the wind blows or not, this is there, and the effect of this imperfection is adding to other effects. But in a concession to past practice, the fact that people have not been using this until now, the committee decided that we should allow this notional load to be treated as a minimum lateral load as long as this ratio of delta over delta zeros is not more than 1.5. Now, what that delta over delta zero, that's a measure of the stability of the structure. It is delta is the lateral displacement, the second order lateral displacement. Delta zero is the first order lateral displacement. So if your structure is very stiff, that'll be close to 1. And if that stability ratio is less than 1.5, you apply this notional load as a minimum. What that usually means is that you won't have to apply it in load combinations that include wind or seismic load. You do have an alternative though. Instead of applying these notional loads to account for geometric imperfections, you could model the imperfections directly in the analysis. That's the alternative you have. And for structures other than simple tiered buildings, that is probably the way you would have to do it, because it's difficult to, well, you could still use the notional load concept, but the constants that were given are really for a tiered building. But for any structure, you can model the imperfections directly in your analysis. Finally, residual stresses. How do you handle that? Well, it's done by using reduced flexural and axial stiffnesses in the analysis. You use an EI star and an EA star in the analysis instead of your usual nominal EI and EA. And the basic reduction factor is 0.8 in all cases. But then there's also that tau sub B just on the flexural stiffness. Now tau sub B will be 1 when your axial force on the member is less than half of yield, and otherwise it will be some number less than 1 if your axial force is larger than that. If you want to avoid the cyclic process of finding your axial force and finding your tau and then reanalyzing and so on, you can use tau as 1 in all cases if you add a little additional notional load in your analysis. Okay. So that's how you account for these effects. And once you've done that, you can design the member using the provisions for individual members, with k equals 1 in computing compression strengths of individual members. So just to show how that looks diagrammatically, here's the direct analysis method. You do a second order analysis, either rigorous or by B1 and B2, the second order analysis. You include imperfections and an elasticity in that analysis. Imperfections, footnote 1, can be accounted for by notional loads or direct modeling. Inelasticity is accounted for by using a reduced EI and EA. And then you compare member demand calculated that way with member capacity calculated at k equals 1. And of course, imperfections and inelasticity are included automatically if you just use your usual member strength, the usual column strength formulas. So it's simple. You just do your analysis, compare it with the member capacity using your usual equations with k equals 1. And this is applicable to all structures, does not distinguish between brace frames, moment frames, whatever. It's a very general method, applicable anywhere. And it may be used in all cases, and it must be used when that delta over delta 0 is greater than 1.5. Then this is the only method that you can use if delta over delta 0 is above that limit. When delta over delta 0 is less than 1.5, there are other options. And one of those, and this shows you just the organization of chapters and provisions in the code. The direct analysis method is in Appendix 7. Then the two other methods that you can use when delta over delta 0 is less than 1.5 are the so-called effective length method and the first order analysis method. The effective length method is in section C.22a and the first order analysis method in C2.2b. Let's look at the effective length method. This is generally similar to the method in the previous specification. And here's what you do. You perform a second order elastic analysis using nominal geometry and nominal stiffness. And again, remember, first order analysis amplified by B1 and B2 is second order analysis. So anyway, you do that second order analysis. Then you apply notional loads of 0.002 y sub I as a minimum lateral load. And this is new. This you did not have to do in the previous specification. But again, this will usually apply only when there's no lateral load, no applied lateral load, because this is a minimum lateral load that you need in all your load combinations. So in combination with wind will usually be bigger than this, so you can ignore it in wind load combinations. Determine K factors for columns and moment frames by side sway buckling analysis, and this is the step that I have no idea how to do, and I don't know if anyone is doing it right, but this is the same as before. You've got to determine K factors. Exception is that you can use K equals 1 if that delta over delta 0 is close to 1. And finally, design individual members using K from step 3 for computing compression strengths. That's the effective length method. So again, looking at that diagrammatically, you do the second order analysis, either rigorous or by B1, B2 there. Then you include imperfections by notional loads, but neglect inelasticity. And again, check the member capacity using your usual column strength equations, which include imperfections and inelasticity. But since you're neglecting inelasticity, you still have to use K greater than 1 here. You have to do K from a side sway buckling analysis, which you've had to do in your previous spec. Finally, there's the first order analysis method. Well, this can be used only when your axial force in all columns whose flexural stiffness contributes to the lateral stability of the structure is less than half of yield. So all your columns that are giving you lateral stiffness has to be loaded to less than half of yield. And here are the steps. Perform a first order elastic analysis. Apply an additional lateral load, and that the magnitude of that depends on your stiffness and your delta over L and so on. Apply a B1 multiplier to the full moment in all beam columns. This is just something to account for local second order effects in your individual members. And then design individual members using K equals 1. Now, I cannot diagram this because this really is, it's a hybrid method. This really is direct analysis by the back door. This just uses some kind of mathematical manipulation to give you roughly the same results as the direct analysis method for typical structures. Okay, so these are the three methods: direct analysis method, effective length, first order. Let's compare them. Limitations: there are no limitations for direct analysis. There are limitations for the others, as you can see. The analysis, for the first two, you need a second order analysis. For the first order, obviously you don't. And again, anytime I say second order analysis, that can be a first order analysis amplified by B1 and B2. That is a second order analysis when you do that. Of course, for the first order analysis, there is that little wrinkle to it that you do need to apply the B1 multiplier. Geometry, for all three, typically you would just use nominal geometry, though you do have another option for direct analysis. EI and EA, stiffness, you use reduced stiffness in the direct analysis method, nominal stiffness in the other two. Notional load, you apply the 0.002 as a minimum load for direct analysis and effective length, and you apply a significantly larger lateral load in the first order analysis method, and that's always additive. And then K for member strength, you use K equals 1 in the direct analysis and first order analysis methods, while you need that magic side sway buckling analysis for the effective length method. So this is a simple comparison of the three methods. Now, let's go back to the conventional approach. You remember that, where we neglect imperfections in inelasticity and compensate by using K greater than 1, and that had these three problems with it. And let us see what happens to these problems under the new specification. First, let's look at direct analysis method, where we include imperfections and inelasticity and use K equals 1. Well, that eliminates all of these problems. The incorrect moment goes away because now we're going to get correct moments. Calculation of K, well, we don't have to do it, and this conservatism goes away too. Now let's look at the effective length method, where we include imperfections but neglect inelasticity, but we still have to use K greater than 1. Well, we eliminate that first unconservative error in the new effective length method, but we still have the other two problems of calculating K and sometimes being too conservative. And finally, the first order analysis method, I can't really diagram it because, as I said, it really is a hybrid method. It is the direct analysis method by the back door. It just uses mathematical manipulation. So there's no real independent logic to it. So generally it has the same benefits as the direct analysis method. So it is a powerful method, but I must advise everyone to do not apply this by rote. The first order analysis method. First, learn the direct analysis method, which really is the basis of it, and then once you're comfortable with it, certainly for structures to which it is applicable, you can save time by using the first order analysis method. Okay, because the direct analysis method, frankly, is the right way. It is the only really correct way to design structures for stability, and it is simple. You do a second order analysis, include imperfections and inelasticity as by the methods that are prescribed, and then you compare that with the member capacity just using your usual column strength curve with no corrections, no further corrections, and use K equals 1. Simple. A word about loading now. When you're talking about stability, you are talking about an inherently nonlinear phenomenon where the response to load is not proportional to the load. So in this picture, the vertical scale shows the magnitude of applied load. The horizontal scale shows member force or moment. And when we're talking about stability, you can see the ratio of R, the member force or moment, will not be the same as the ratio of the loads. Clearly, you can see that. And that has certain implications. For LRFD, it really has no implication because you apply your LRFD load combination, you find your resulting forces and moments, and you design for that. No problem. But with ASD, we do have a problem. You cannot apply your ASD load combination, find the resulting forces and moments, and then use that for design. You can't. And let me tell you why. The ASD process assumes that the ratio of ASD and LRFD member forces and moments, is the same as the ratio of loads. And that is true for other types of structures, but not where stability is the issue. Typically, the ratio of ASD to LRFD load might be 1.5 or 1.6. Well, this ratio is a lot more than that, as you can see, because of the curved response. So, if you used this force, R sub ASD, and designed by ASD for that force, you're going to end up with a member smaller than what you would get by LRFD. And with a smaller member, you have less reliability, less safety. So this is what you're required to do for design by ASD. You start with your ASD load combination, and you multiply it by 1.6. You analyze your structure for that increased load of 1.6 times the ASD combination, which gives you forces and moments that I'm calling R sub 1.6 ASD. Now you divide that by 1.6, And that gives you the forces and moments for design by AISC. Because this will give you the same, roughly the same reliability in your members that you would have got by using LRFD. And as you can see, this R sub ASD design is bigger than what you would have got if you just analyzed for ASD. You can see that. So this is what the specification tells you to do if you are using the new specification using allowable strength design. Finally, let me list the members of AISC Task Committee 10, which is the Committee on Stability. And you can see that it is a good combination of practicing engineers and professors. And I must mention that much of the early work on the 2005 stability provisions was done under the leadership of Joe Ura from the University of Texas, who was my predecessor as chairman of this committee. And finally, let me just say that the paper in the 2007 North American Steel Construction Conference proceedings for this T.R. Higgins presentation includes in an appendix a model specification written exclusively around the direct analysis method. You know how right now the method in the base spec is the other methods and the direct analysis is in an appendix. Well, in this model spec that's in an appendix to this paper, the model spec is the only method. The whole spec is written around the direct analysis method. And this model specification is a tentative preview of the stability section of the 2010 AISC spec. We intend that in 2010, which is the next spec cycle, the basic method shown in the specification will be the direct analysis method. And other methods will probably be permitted, but they will be off in appendices. The basic method will be the 2010, and that I think will make the spec a lot easier to read, a lot easier to use, and to see how it might look, just go look at the appendix to that paper. And I think it's available on the website. And thank you.